You've learned about some more angle relationships involving circles, so now let's look at some segment length relationships. Here you can see two intersecting chords. There's an equation that represents the relationship here for the parts of the chords that are intersecting. We can multiply each part and set it equal to the product of the other parts of the other chord. Let's look at an example of this. Here we have a chord that has a length of 11. One part is 3 and one part is 8. And here we have a chord with a length of x plus 4. One part is 4 and one part is x. We can set this up into an equation so that it says 8 times 3 equals 4x. Multiply this out, 24 equals 4x, divide by 4, and x equals 6. We can see a proof of this in this diagram here. We know that these two angles on the inside, both labeled theta, are congruent because they are vertical angles. And then these two angles right here, this one phi and this one phi, they are both congruent because they intersect the same arc. And remember, we know that an inscribed angle is half the measure of the arc it intersects. Going back to similar triangles, we know that two triangles are going to be similar if they have two angles in common. And once we know that two triangles are similar, that then tells us that our side lengths are proportional. Knowing our triangles are similar allows us then to set up proportional relationships where we can say that A is to C as D is to B, and we can cross multiply and have our relationship where, oh, sorry, A times B equals C times D. All right, let's look at another example. We have intersecting secants. This diagram looks a little more complicated than it is. We have two parts to the secant that we're going to look at. We have the part that's on the outside of the circle, from the outside of the circle to the intersection point, and then we have the part that's on the inside of the circle, but we are going to look at that in terms of the whole thing. So we have what's on the outside versus the whole thing. And we will multiply those two pieces. Same idea with the other secant. What's on the outside, part C, compared to what's the whole thing. We will multiply that. Let's look at an example. Here we have the outside is 3. The whole thing would be x plus 3. And here we have the outside is 4. The whole thing would be 4 plus 8, which will give us 12. So we end up with 3 times x plus 3 equals 4 times 12. Let's multiply that out. 3x plus 9 equals 48. 3x equals 39, and divide to get x equals 13. This gets a little more complicated when x is the value on the outside, because it turns into a quadratic. So let's just take a quick look at that. We have now x is the outside, the whole thing is x plus 13, and then we have, again, 4 and 12. So when we multiply this out, we end up with x squared plus 13x equals 48. We can subtract 48 from both sides and factor this out. We end up with x plus 16 times x minus 3 equals 0. And when we subtract to solve, we end up with two answers. X equals negative 16 and x equals 3. Now, we know from context that this problem is referring to length. So even though algebraically both of these answers work, we know that the x minus 16 does not work in this problem. Okay, one more thing to look at. This This can also be proven with similar angles. I will let you take a look at that on your own. You can pause the video if you want to dive into it, or just take a quick glance to look at where the similar angles are coming from. Same idea as before. And one more thing to look at, the relationship if we have a secant line. Again, notice it stays the same, the outside times the whole, but a secant line and a tangent line. This also has a relationship similar to outside times the whole, except with a tangent line, the outside and the whole represent the same segment. So that is where the c squared comes from. Let's take a quick look at that. Here we have the same setup as before with the secants. 4 is the outside, x plus 4 would be the whole, and over here we just have the length of 6 to represent my tangent segment. So I will set this equation equal to 6 squared. When we multiply this out, we get 16 plus 4x equals 36. Subtract, so 4x equals 20, and divide to get x equals 5. And there you have the relationship between two chords, two secants, and a secant and a tangent.